Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Today we're going to study something that has fascinated me for a long time. It's awesome. And you might think, really? Winds. What causes winds? And if you look at the Earth, it has patterns. The winds have a pattern, but why? Why do they have a pattern? Well, let's take a look at this sketch right here, and I want you to fill this in as we go along. And because on the right, there's some important things, and it all comes down to convection. Remember, we talked about that in the last video about convection cells. Is right here at the equator, we have these two things called Hadley cells. Write that down. Hadley cells, and on either side of the equator. And then further on either side, we have the feral cells. And then further up, we have the polar. And let's continue labeling this, and we'll talk about why what happens. And if we look on the left side, in the equator, we have what are called, on either side of the equator, the trade winds. In the middle, though, I want you to write doldrums. And then we've got, on either side of this, we've got the westerlies. You see that next up there. And then we've got, at the top and the bottom, the polar easterlies. And so the Earth, if you look at the wind pattern, this is the pattern that it has. That in general, like we live here in Houston at about 30 degrees north latitude, we have a pattern. We're kind of on borders. We're kind of in a weird place. But in most of, say, North America, it's primarily the weather comes from the west to the east. Not always, but it comes from the west to the east because we're in the westerly area, right? Now, by the way, in the southern hemisphere, it's the same way. This is coming from the northwest. Notice down here, it's coming from the southwest. And then it's flicked around. There's the trade winds moving this way, and we're in this border where they kind of fight each other, and that's how, like, we can get hurricanes and all kinds of exciting things. But why? Why this pattern? So why this pattern? Well, let's draw a sketch. All right, I'm going to try and draw the Earth now from the equator, where this is the equator. And the sun comes down, and the hottest part, remember we talked about solar density in an earlier video, the hot part is the equator. And so if the hottest part, what's going to happen is this is going to heat up, the air, hot air rises, and it's going to do this. So if this is 0 degrees, and this is 30 degrees north, and this is 30 degrees south latitude, it creates a convection cell. And actually, what does it do? It then rotates and comes around this way. All right. And what turns out, what's happening is typically happens to happen over the ocean. This is moist air, and so this becomes, because it's water and it evaporates, this tends to be wet. All right. So this whole area of the Earth tends to be tropical, rainy, etc. Right. And then as the hot air rises, it comes around and it does this. And what descends is dry air, typically. Now, you might say, wait a second, Mr. Bergmann, it's not dry here at all in Houston. We have a weird microclimate thing going on because of the Gulf of Mexico and some of the things, and we're kind of right on the border. But by and large, if you look at the Earth, at around 30 degrees north or south, that's where you find the deserts of the world. The Sahara Desert is here. Even if you don't go further west from us, you get the Arizona Desert, the Mojave Desert. You get all kinds of different things at these 30 degrees because dry air descends, and dry air, there's not much moisture in it. And this is called the Hadley cell, right? And we get this pattern. It doesn't explain, by the way, when we talk about it, the direction of the wind moves from east to west in this area. All right, that's going to talk about that. There's another variable we haven't talked about. So that's the Hadley cell. All right, so get that idea that we have this convection, and this right here, this particular thing called the Hadley cell, Hadley cell. This Hadley cell creating this pattern is the primary driving agent, well, of wind in the world. So let's talk about those three cells for just a moment. The Hadley cell, the Hadley, the polar, and the feral. And I'm kind of going in kind of a weird order. This is the one that's at the equator we just talked about, right? And it's a convection cell. Hot air rises and creates this. This is like the most dominant pattern because it's super hot. The polar one's weird. Okay, what you have is I'll say hot-ish air, Nothing's super hot at the poles, right? And this is at 60 degrees. Again, this depends on the time of year, so but roughly 60 degrees. And it's hot-ish air rises at 60 degrees. And then they also make a mini convection cell that's not as strong as the Hadley cell because, of course, the temperature difference isn't as great. And the feral cell, that's the one in the middle, right? This is caused by the other two. A lot of people have called this, first of all, it's the area of mixing. This is where the air mixes so much on the Earth, and this is where you can get wild swings in weather. But what's causing this to happen is these other two. Think of these, people have often called this this is like a gear on a motor, right? So you've got a gear on a motor, one thing turns the other. So these two here are turning, and then it's mixing the air in the middle. So it doesn't have like a convection cell. That's the way, by the way, why if you look at the image over here, it's in the opposite direction. See, these two both go from, if you will, the middle to the north or to the south, depending on what part of the globe you're on. And it makes sense, hot air rising closer to the equator, or even on the equator, and then rising and creating a thing. But here it's flicked, but it's because it's acting like a gear. So that's why we get the mixing of the Earth. Now, so you might ask, so why are they moving though? This is the question that kept bothering me. It's like, why do they move to the east and to the west and all that stuff? And that comes down to an interesting concept. Not only does it rise and fall in sort of a nice pretty pattern, something else is going on that's really significant. And it's something called the Coriolis effect. And instead of me trying to explain the Coriolis effect, really the best explanation I've ever seen on the Coriolis effect, well, let's watch.
What's going on here? Every time I throw the ball straight, it seems to bend to the side. No matter what I throw, no matter how straight I throw it, the ball seems to be curving. Maybe it has something to do with this. That whole time I was spinning, which is why it looks like I'm about to puke. That curve is created by the Coriolis effect. You may have heard that it makes water in the bathtub spiral down the drain a certain way, or that it determines the way a toilet flushes. That's actually wrong. Those are not caused by the Coriolis effect. But the Coriolis effect is what makes hurricanes spin, and it's the reason why Jupiter's Great Red Spot is spinning the way that it is. So what is the Coriolis effect? Well, it's what happens when objects moving in a straight line appear to curve because you are rotating. And it affects all kinds of things. It bends the paths of missiles and sniper shots. But how does it work, and how does it create hurricanes? Right now, it seems like the ball's curving, but let's take a look at what's really happening. My friends and I put together this little experiment using a sort of spinning seesaw. Here, the camera's standing still. It's just hanging from the ceiling. And watch what happens. From the moment the ball leaves my hand, it's just going straight. Let's watch that again, frame by frame. Keep your eye on the ball. You can see it travels in a perfectly straight line. But what if you're spinning with the seesaw? Look at what happens when you rotate the footage so the seesaw stays sideways and everything moves around it. Now let's follow the path of the ball again, but from this new perspective. The trajectory looks completely different. Now let's watch this one frame by frame. From this rotating perspective, it totally looks like the ball is curving. That's crazy because you already saw that exact same throw. Watch it again on the left. The ball is going straight, but on the right, when you're rotating with the seesaw, the ball really looks like it's curving. You might be thinking, why should I care? I don't spend a lot of time on a spinning seesaw or on a merry-go-round. But you kind of are on a merry-go-round. The Earth is constantly spinning. Have you ever seen someone in a movie making fine adjustments on their gun? Well, one effect they're correcting for is the Coriolis effect. The longest sniper shot, which was over 3,000 yards, would have had to correct for a 1-foot deviation due to the Coriolis effect. So how does the Coriolis effect create hurricanes? Hurricanes form when air rushes from all directions into a low pressure region. So imagine there's a low pressure region between the two of us. Air is going to rush toward the center. Let's see what that looks like from space, from our camera that's hanging from the ceiling. It's not spinning, so the air, or in this case the balls, are clearly going in a straight line. But if you're rotating with the Earth, or with the seesaw, you'll see the air bend to the right. In the northern hemisphere, this creates hurricanes with counterclockwise spirals. In the southern hemisphere, it does the opposite. It creates hurricanes with clockwise spirals. This storm on Jupiter, which is actually bigger than the Earth itself, has been spinning for at least 200 years, largely due to the Coriolis effect. So when you're in a rotating frame, the Coriolis effect seems to exert a very real force on objects. But there is no force. What you observe is just a result of your perspective.
So hopefully that video kind of cleared it up for you, right? It's just, we've got the Earth spinning, but since the Earth spins at different rotational speeds, right? It's faster at the equator than it is at the poles, or even here in Houston, that when you have the air, or the ball in the picture that video that we watched, it's going to appear to curve. And that's why we get the curved nature of the winds that we talked about. Right? Let's review our image here of the different winds. So right in the middle of the ocean are the doldrums. I think this is a fascinating place, the doldrums. This is where there's hardly any wind, because what's happening is the air rises, and as the air rises, it creates sort of a void, and then if you're a sailboat guy, or, you know, bad news. But then you've got the trade winds, you know, on either side, and you can count on those winds working. And then the other interesting place is at where the Hadley Cell drops, where there's that barrier between them. We've got an interesting set of latitudes, and now it's something you haven't seen this, we haven't talked about this, but there's a thing called the horse latitudes. The horse latitudes is also a place where the wind is dead, typically. Again, there's changes day to day, whatever. But in the horse latitudes, you can have something very interesting. You know they call it the horse latitudes, where there's hardly any wind? Is because back in the day, when boats would travel from England and Europe, whatever, to the Americas, they would take their boats across there, and sometimes they would get caught in the horse latitudes, no wind, and because they were dead in the water and they couldn't move their boats, they had to throw the horses overboard because they were drinking too much water. So they call it the horse latitudes. I thought that was pretty fascinating. And then, of course, as we go further north or south or whatever, we get the westerlies, etc. But notice the curve, and the curve is caused by the Coriolis effect because of the rotation of the Earth. So I want you to summarize so you understand, why do we have the different shapes of wind patterns? It's really a combination of the convection primarily caused by the Hadley cell, to some degree by the polar cell, and then the gearbox thing with the feral guy, and then the Coriolis effect with the rotation of the Earth, which creates the wind patterns of the Earth. Houston, we've got no problems, because, well, you guys are awesome, and we'll see you in class.